All right. Yeah. So we're back on training in AI. So we're following this. What we have so far, as we'll get started here, is let's just make sure that we have the right code and nothing's been changed. Okay, it turns out a bunch has been changed. So let's just, we're going to open our programming language. Uh, I'm doing it in Julia, not Python. And the reason for that is just so that I understand, if you try to learn something by copying, if you take it out of context, maybe you learn it a little bit better. Anyways, let's just update this. Then so we're training an AI. So that's the first part of this is this code. But then the second part of this is sort of the more clickbaity part of this, which is I have this repo, and we're going to rerun this. I'm actually going to I am going to open up another one. I'm going to delete all my old transcripts. So we're on sort of the second iteration of this, and we have this, which has all of our transcripts in it. But this code was a little bit messy. And I kind of want to improve it. It does take a while though. So we're just gonna leave this because I think I have enough space on my computer. So I have a new repo and this is GitHub and then I forget what it is, what it's called. It's transcript grabber. Okay, and we are just going to git clone oops. We're just gonna clone that. Get that. And yeah, in here is the README, and the README has this. The thing about this is we don't actually want this. We want this. But first we need to I kind of wanted to do all of this. Oh yeah, okay, wait. Right, we are going to run this. So okay. So let me go back to the AI part. We can close this. So the AI part, oh, it's still pre-compiling, so that's okay. Something happened. All we're doing is we are getting the transcripts, and those transcripts will be used to. Yeah, dude, this thing is so broken, it's crazy. Okay, we're almost there. Okay, so I don't actually know what's all is in here. This is just some analysis, and then the thing that builds the data set is this. So we will do that. Let me move all of these functions up to the top. The thing is, I really wish it was multi-threaded. If I had the time, I would do some fancy thing in Rust where I look into the YouTube DLP source code, see how they do it, and then either use that DLM thing or, do something that's just a little bit faster because it is really slow. But it's just like I don't have the time. Right. So this is actually a useful function. This is probably the only useful function actually in this code. It gets dskip, where it just doesn't error if it finds anything. Honestly, don't know why those aren't in the standard library, but no matter. Okay, so let's just run all this stuff. So we make all of the data. So this just makes a bunch of directories. Dude, why is it Julia is such a broken fucking language? I bet the same thing happens here. Exactly. It's like, how is this still a problem? Something needs to come along and beat this, because it's just so stupidly broken. They say they precompiled it, and then it turns out they lie to you. Anyways. That's why I couldn't stand this shit. The thing is, it's so much better than Python. I mean, Python is just such garbage. The tooling, the language itself, it just sucks, man. The REPL, everything about Python is terrible. In any case, a lot of this is just freaking stalling because we're waiting for dumb stuff. So let's just watch this and start to try to understand the attention mechanism. All right, so he goes over the data. Okay, wait. All right, so let's just get this started really quickly. Okay, this is my YouTube channel ID. Oh, we need to get the IDs, I guess. Did we do it? I don't know what's going on. What? Oh, we gotta... Oh. Wait, no, what? Grab command. That's what we want to do. And of course the fucking language server is broken too. Whatever. Wait, write info JSON, write. Get IDs. That's what we want to do. And this writes it to... Okay, so that's what we wanted to do. Oops. So let's delete these and just run this. Okay, so this is all my video IDs. Okay, and then we do this IDT. I think it's IDTFN, I think. Okay, so we get this, then we do this. Okay, now we have everything. And now we write this to there. And now we're going to get all the metadata. So that's the command. But does that run it? Oh yeah, we have to uncomment this and then we have to run it. But do we run it in here? I think we don't. I think what we do is we just run it outside, because then otherwise it captures the standard out, which I don't know if I wanted to do that. Okay, so here we go. So this writes all of the things into there. So now if we go into metadata, it's going to be downloading Yeah, all my, right. So this is all the metadata. So that'll take a while. And then after that, we'll download the transcripts. But let's get back into, okay, so finally it ran this code. I wouldn't be, exactly. I wouldn't be surprised if it's still got a problem with it. You know what, dude? I'm going to do something. This is just getting back into my old dumbass ways, but we need to like 11.1 is broken. Let's just do because it's LTS. So if I, because what am I on the default? The default is 0.6, so it's 2 minors behind. Oh wait, why am I on nightly? What? Dude, why do I have nightly? Whatever, I don't care. As long as it also gives me the correct. So we're gonna have to pre-compile this, but I can't. I have to imagine that it's. It's probably because there's open Julia. Wait, Julia up default LTS. What? Julia up add LTS. Oh, it's 0.7? Then why is this list out of date? What the hell? Goofy Goofy But then it's gonna. Dude, there's so much bullshit. People actually like doing this stuff. I don't know what all these warnings are. Whatever. These are the videos. I mean, they're. Presumably that was the issue. They fixed a bunch of issues. I mean, I like that on using it does, at least it does parallel. Like, before it used to just do it in serial and it was a total mess. Alright, cool. So let's just do this. I think I'm going to close it and reopen it just in case there's a pathing thing. I think it's getting them all. I think it's just some weird thing is happening. It's just such a joke, bro. Like, you just constantly have to do this for fear of outdating this bullshit. Okay. So now if I do this, let's just make sure it's got the, okay, obviously it's fucking stupid bullshit. But then I bet if I do this, it's broken. See? Okay. Let's hope not. Let's hope not. Hoping for the best here. Okay. So now once this is done, I can close all of this and make sure that everything is okay. And then we can finally build the data set. I should have done this in a terminal. Okay, well, while we wait, let's try to understand attention. Port. Okay. So I want to start here.
Okay, so we are almost ready to start writing the very first substitution block for processing these interviews. Before we get there, I want to get you used to the mathematical training that is used in the self-attention research program. And it's connected to the hardware. And so I'm going to just go ahead and just get you used to this operation. So let's create EITS. And we have a time component and we have some information like entry in sequence. So we
Please work. Nice. So then let's just close this. So we don't have this. God. Okay, well, whatever. We got most of them. So let's close this. Let's reopen this. Okay, now we can run this. But I feel like maybe it's just gonna fail. I don't know. We'll have to see. But I have a feeling it's gonna fail. Look at this log. For the requested language, auto subs. Okay, anyway, so now what we get is this JSON file that's massive, and then we can concatenate all that into a string using the code that I wrote. So now what we want to do is open up the actual neural network and start to play around with this. I hate this dark mode, but if we toggle the theme, my cursor gets invisible. I don't know what happens there, but it becomes invisible. Let's see, maybe it's better now. Nope. So stupid. Let's see if there's a... Maybe that's fine. No, it still gets hidden. You guys see that? I don't know what the hell that is. Whatever. Okay, so let's do this. It's starting the language server, but let's just see. Please work. Please work, guys. Right, we kind of want to start here, don't we? The weird thing is that we need to dig into this because it says how do I sign in? Damn, YouTube flagged me, bro. That sucks, dude. YouTube is clamping down, man. And the thing is, guys, in general, YouTube is actually pretty sucky. Like, it is a pretty bad platform in general. Anyways, let's see, is this done? I guess not. Okay. Of course. Okay. Wait for all this. Okay. All right. So now, you know what? Just in case, because you never know what's gonna upset this stupid fucking language. I'm going to restart it because sometimes if you update, it causes problems. So now, if there's any compilation thing, I'm gonna freak out, dude. Okay, I think we're good. All right, so this is the code that we have so far. We have this thing that makes a data set, and basically what it is it takes a block size and it takes a bunch of words, which in this case are names. It's this data set of names, and the original point of Make More was to basically generate names. And so then this is the code that generates it. This is a plot that plots two-dimensional embeddings, but honestly, it was kind of more just, you know. Okay, so here are the names. This is how many names we have. This is the character set in the names, and then this is a extra token for marking the start and end of names and generations or whatever. So the vocab size is then all of these characters. So when we train on our data set, which will be soon. Okay, so I guess we can do it now. Okay, so we're gonna make we're gonna update, close it, restart it, and then we can use it. Okay, cool. Okay, so now we no longer have to do get IDs. We no longer have to do this. We no longer have to do this. So let's just run. All of this code. And then we don't need to read any of this metadata. Metadata is not that important. Oh, that's what I'm saying, bro. Like, why the hell is that compiling something? What are these? These are the TXTs of the metadata. Okay, so here's what we want. So this compiles the data set to train on. So we get all of the transcripts we have, which is now down to 156. It used to be 177 or something like that. But in any case, okay, we read all these JSON things. We get the text transcript of it, which just concatenates everything. Make a map, make a dict, and then write data set. Okay. And this is what we want to read in. The annoying thing is that these transcripts actually distort it because anyways, it'll be interesting to see how this data set stacks up. This is how many bytes were written. Can we open this in File Explorer? How big is it? It's bigger than the Shakespeare, but it's smaller than the internet. So we can definitely say that. All right, so we have our data set. So wait, let's train a neural network right now. Come on, let's just get back up to speed. So okay, so then we build an index from our alphabet, which this is a character level model, to an index, and then we make it a dictionary, and then we reverse it so that we have an index to a letter so that we can decode it. So this is an encoder decoder thing. This is a parameter that defines basically our context size, which is how many letters we're using to predict the next letter. So we're using 3 letters prior to predict the next. Then we're going to shuffle them up so that we can build this 3-way split of 80, 10, and 10%. So the train set is what we train on. That's 80%. Then we have a dev set, which is basically what we use to train the hyperparameters. And then the test set, which we just do at the end, and then we report that number. Okay, so then here's where we construct the model. So this is some basically hyperparameters that are the framework for how big the model is. So the embedding dimension is that each character gets mapped to 10 numbers that basically tell the neural network what, but the thing is the embedding gets back propagated through. So as the network learns, the embedding will change. And we saw that where we plotted in maybe the last episode or the 2 episodes ago, we plotted basically before we train the neural network, we visualized the embedding. Wait, we can just do that right now. So how do we do that? The embedding plot. Okay, so let's just make the model. And wait, let's make it 2. I'm going to make it 2. We'll get to the rest of this in a second. And then we'll do embedding plot. And what we'll see is that there's no rhyme or reason to this at all. But if we train it, we'll see something like the vowels get put in a specific place. Can we do this again, actually? Okay, so in this case, Q is amongst the other letters, which is, Q is a very different beast. In any case, so we got that. Okay, so then the rest of the model. The rest of the model is, so let's go back to this 10. We don't need this plot. We'll train this network. Is we have one function in the middle here that basically changes the embedding to be in the form that can be accepted by the dense layer, which is basically just a matrix multiply and a bias, and optionally a nonlinearity. So you can see here that we have one nonlinearity in this whole model. And that's important, right? Because nonlinearity is what makes this whole bundle of linear algebra actually do anything useful. And I've said this before, and I'll say it again, but I feel like the 20th century of science and mathematics, well, up until maybe the 70s and really the 80s, the 20th century was studying linearity. And after that, we are now in sort of the age of nonlinearity, where we found that, simple nonlinear rules lead to all the behavior that you see in the world. And it's really the study of the nonlinearities that has led to so many breakthroughs, like from small things like cellular automata with Stephen Wolfram, and to big things like neural networks. Nonlinearities are sort of at the center of that whole shebang. All right, so let's make this model, and I'll quit talking nonsense. So, okay, so here we're just taking a batch. So let me just taking a random, just taking a batch. Do we have batch size? Where's batch size? Okay, batch size is there. Okay, so we just grab. So this is what a batch looks like. We can make this 32 if we wanted to. So this is what a batch looks like. It's like 32 by 3. And so what we can see here is that if we look at, oh, I guess I don't have a good print to print this out. I guess I deleted it. But basically, I mean, it's not that hard. What we're doing is we're taking, so 1, if we do I to S of 1, we get a dot. So what we're saying is in this first row here, we have 3 dots. And if we take Y1, Y train 1, oh, wait. Yeah, that could be right. Let's see, where are we? Where are we? X, oh, X. Okay, yeah, it's the same. So what we're saying is that that the first XY pair is going to be trying to take X1 and map it to Y's 1. So this is the pair. We're trying to take 3 dots and predict that the next character is a Z. Okay, so that's what we're doing. That's just an example of the model. Here and I can actually do, I think, this. I think I can make this even better. I guess not. Wait, did this fail? No, that worked. I don't know why that worked and the other one didn't. Oh, you know what? Wait. Oh, because this returns a chain. Oh, indexing multiple things gives a chain. That's kind of interesting, actually. So that means that HF is just, let's see, model 1 to 3. But we can't reverse it, right? Wait, but I don't think we need to because it's a chain. So then we should be able to just do HPF is equal to model 1 to 2. But the reason why we can't do that, oh yeah. So the problem is, if we want to get the post-activation, meaning the post-nonlinearity part, this is what we'll do, is we'll do HF of X. So this is after the tan H. But the problem is, so what we can do here, whatever, this works. Anyways, the point is, what we want to know is what happens before the nonlinearity. So that's what this function does, HPF. And we say H equals HF, so this is the hidden states of it. And then we can do a histogram. So this were a couple plots from Andrej, and the and for any one of the hidden neurons, if it's all black, then I think it's none of these examples excited it. So meaning it's basically a dead neuron. It's not doing anything. And I think that's, is it if it's 1 or is it if it's, yeah, if it's 1. So if there's a streak of light across this, then we're going to see a dead neuron. Because what we're doing is we're taking the hidden states after the tan H, and remember, tan H scales it from -1 to 1, so that's why we take the absolute value here. This histogram shows us where this lies, but this is H. But remember, we're not using tan H, we're using ReLU. We're using ReLU. That's why we see this. Because that means that there's stuff dead before 0. And actually a lot of it. Okay, cool. So that's just some visualizing the activations. Now here's where we calculate some of the loss. Okay? So this is where we calculate the training loss. And remember, we just initialized this. So this is actually pretty high, 4.09. All right, so we set our batch. We define this struct. It's just some boilerplate garbage. called a flux data loader, and it just allows the thing to iterate over the train set and the whatever. The problem is in here, this is kind of janky. I don't know what a better way to do this is, because I think probably what I'd want to do is, because let's say we got oops. Oh, fuck. Okay, so now we do rand. So this is a batch, and then we do at b allocated stack b dim 1. So see, we're allocating memory here, and if we just take b size of b, okay, so whatever, we're allocating though. That's the point. Oh, that actually checks out. That's about right. So we're allocating on every single step, and that's terrible. So maybe what we want to do is do maybe that's what we want to do. So if we do this, so if we do, oh, do I need to pair this up like that? All right, so now we have a loader. So we can go first of loader. And so we get a bunch of indices. And so what we want to do here is, instead of stacking the X batch, what we want to do is we want to do X train, X batch, like that, I'm pretty sure. So we got XTR of, so let's just say X1, Y1 is equal to the first loader. Okay, so we have this. Now we want to do X1 like that. And then we get a matrix. So that's a view. And we could actually do, I think, view. I'm pretty sure we can just put that in like this. And then we save some allocation, right? So we've changed the data loader to be a little bit faster, I guess. All right, so let's see if it works though. All right, so we set up the optimizer, and I just want to stick with gradient descent. I tried to use Atom, and Atom just like didn't work. I don't know what the deal is, but it just didn't work. Let's just train for one epoch and see if it works with the view. It should be faster, but I don't want to go into measuring it because I really don't care. The point of today's lecture, and today, we're trying to understand attention. That's the whole point today. Okay, cool. So it seems like it works. We trained for one epoch, and it seems like it's pretty good. Let's train for 3 more. All right, that's pretty good loss. So we can plot these losses, and we can see here, I think this is log 10 losses. So that's what the log 10 loss looks like. It's pretty noisy, and the reason for it being so noisy is the batch size. I'm pretty sure if we take this batch size and we make it 1,000, and then we rebuild this data loader, keep the losses, and then we just run it for 3 more epochs, we're going to see here, let's just plot it. So we plot it and see here how much narrower the band of losses is. It's because we're taking so many more examples. That's why I feel like it makes way more sense that as you start to converge, you probably want to increase the batch size dynamically. Just like you want to drop the learning rate. As you get converged, you want to drop the learning rate and you want to increase the batch size. Anyways, that's what I would do. But I'm sure everyone's thought about this already. Okay, anyway, so now we're going to do our evaluate on the whole set. So this is the batch size of everything. So basically no batch. And we're getting 2.12. And then this is the development loss, or the validation loss. It's 2.14. And we saw that, from Andre said, if the losses start to spread out, then you know that you're starting to overfit on your set, which in some sense is a good thing because it's learning. But obviously, you don't want it to overfit, so you don't want it to diverge too far. But it is a good sign that at least some information is being extracted from the training set. It's not like totally random. And the fact that the dev loss went down over time is also a good sign. So meaning it's generalizing a little bit. Okay, so here, what is this? This is evaluating the trained. Okay, so yeah, so this is what we were saying. So this isn't tan. So okay, I guess this plot doesn't really work. This plot doesn't make sense for non-tan H, I guess, because what we want to do is probably. So wait, can we do the histogram of? So a ton of these neurons are 0, but it doesn't seem like for a batch of 200 that there's any row that is completely ones, meaning that at least the neurons are still alive. Because if you had a row of all white, then it would mean that it's not activating ever, and that's not what you want. All right, so let's look at what some of the names are. So the names Janae, Jory, Mione, Harley. One of my best friend's dog's name is Harley. It's a great name. Anyways, so these are looking pretty good except for that. Ali Lay Rhea. Anyways, I'm pretty happy with this. The thing that I did notice is that if you switch from TanH to Relu, I did get better names, I feel like. Okay, so then we started going to the math of batch norm. Honestly, I was like sussed out by batch norm. Layer norm seems way better to me than batch norm. Like, batch norm seems so sus. Like, why are you coupling a batch together? I don't like it. It seems sus. Okay, here's where we started to get into attention. So now we are at the start of the lecture today. So okay, so let me just try to recount what's going on before I watch the video. So let's just we got this. Okay, so the idea is we are trying to find a way to so let's say that let's say we how do we want to put this? I actually don't understand why we need a lower triangular matrix, because what is the block size in this case? All right, so I'm going to go P, and then we're going to rewatch this part and understand why it is that, because if you have a block size of 3, for instance, I mean, why aren't you always using... Anyways, we'll figure it out. Okay. All right. All right. So let's get it.
Up to 8 tokens here.
Right. Okay. Right. Okay. Okay. That makes sense. But this is specifically for decoders. Okay. All right. That makes sense. So basically, the embedding of the fifth character is conditional only on the things before it. But in this setup, the block size is 8, right? So, hold on. So let's just start here. Uh, oh. But in this setup, the thing that I don't understand about this masking thing is in all of these cases. So, okay, so just to be clear here, if we wanted to get the embedding, so let's make the batch size 1 for right now, just to be clear. If we wanted to get the embedding for a character, then we'd go x1, okay, so this is the embedding of the first character. Okay. But the thing is, in this case though, you're still using all 8 of these embeddings. So wait, can we do? We're still using this whole matrix to predict the 9th thing. So that's why I don't understand why you can't have future tokens talking to each other. If I understand correctly. So I don't see why we need to mask out future tokens. Shouldn't they be allowed to? Let me just talk to it. I'm trying to understand self-attention for transformer models. And right now I'm going through the Andrej Karpathy series. And he's building a character level model. And he's talking about the masking during the embedding stage where you only allow previous tokens in the computation of the embedding. So you have this lower triangular matrix. But what I don't understand about that is that if you have 8 tokens, in this example, there's 8 tokens. So the shape of his matrix is batch by time by channels, and it's 4 by 8 by 2. And so that means that the time channel is 8, meaning that there's 8 characters used to predict the ninth. That's my understanding, at least. So I don't understand why you need to do this lower triangular thing, because you should be allowed to use. I don't understand why an all-to-all embedding is disallowed for the decoder. Okay, so okay. Okay, let's keep going.
Third, second, and first. So it's only so information only flows from previous context to the current context. So what is the easiest way for tokens to be interpreted? The easiest way I would say is okay, clear up previous token, and I'd like to is to just do an average of all the preceding. But this communication is extremely lossy. We've lost a ton of information about spatial arrangements of all those tokens. But that's okay for now. We'll see how we can break down into math later. So now what we'd like to do is, for every single batch element for every T token in that network, we'd like to now calculate the average of all the vectors in all the previous tokens and also in this token. So let's write that out. I have a small snippet here, and instead of just fumbling around, let me just copy paste it. So in other words, we're going to create X and because backwards is standardly the term that you will use when you are just it's just backwards. It's like
Yes, there's a word at every T. Okay.
This outcome. Now the trick is that we can be very, very efficient about doing this using matrix multiplication. So that's the button. Let's work at the 22.
Right. We know the punchline here, right? Like I don't even need to keep watching this because we know the punchline. Let's do this. So we have the same thing as his setup. We have a lower triangular matrix of ones, and then we have some random b, and then we do the matrix multiplication. What we're gonna get is the sum of all past elements, right? And so what we can do here is we can just divide each row. We're gonna go across each row by the axis number. So this is actually the fastest way to do that. What you could do is what he does is I think how does he do it? He goes first. He does the trill. So he does the trill. Then he he's oh yeah. So right. So it's going to be a which is always 1 divided by the sum across that row. So basically that's how you get 0.5 and then 1/3. But anyways, that I think is more inefficient, but anyways, you get the same result. You get this weighted average thing. So so see if we do this. So okay, so that's what we get. Or here, I'll show you. So okay, so A was 1s, and this is B. Where's B? So B. Okay, so B was this. So if we take, so we get 6 and 10 on the first, then 6 plus 3 is 9, so that divided by 2 is 4.5. Same with 14 divided by 2, that's 7. So we see here, and then what is this, 10? 10 over 3 is 3.3, and then what is this, 12, 22, 22 over 3 is 7.3, so there you go. All right, so do we have that part yet? So way. So do we have t? So way is going to be uh, bit trill of okay, so ways is equal to so here's where we're at. So way is bit trill of oh wait, no, but it's gonna be not bit trill. Then it's just gonna be just C, I guess. So so way trill of bit trill of t by t. And we get exactly what he has. So there you go. So that's way. So now we want to do way times x. Do we have x though? What is x in our case? Oh, it's this capital X. So we'll return this to be 4. Not that it matters. It doesn't matter, just to be clear. But then let's multiply this by x. And I believe it's because of... Right, so he's going to show the broadcasting rule here. But if we were to make this... Wait, so this is 8 by 8 times 8 by 2. So if we were to do this, 1 colon colon, then we get something. Right, so I don't know how broadcasting rules actually work, but let's see if this works. Oops. Oh, how do we set this up then? Can we? What if is it anti-commutative or is it non-commutative? Yes, no, that doesn't work. Let's see if we permute dims x, and then we do a 2, 3, 1 thing. This x prime. Then we do an xp. What's the dimension error there? 8 and 2. Because what we're getting is a t by t times a t by c by b. But then this is broadcast. What are the actual broadcasting rules in Julia? That's my question. I don't know how it works. What if the... Oops. Right. Well, okay, so that's never going to work. So we definitely have to broadcast. Let's try... I would assume that this is the way to do it. Because what are we doing if we were to write it as a for loop? We'd say... And how do we iterate? This should be 1 to 4, right? So we do for b in this, and we do... But what is the size that we expect out of it? So wait, so if we were to change way to be... Add dim. How do you add a dim? Okay, so now we have a WAPE. So now if we do WAPE times X, let's make it broadcasted then. Wait, I think this is the wrong. Wait, this is wrong, right? I mean, but it's doesn't matter.
Will be of T by T multiplying T by C. Exactly as we said. Exponent 2. Identical to exponent. So we can see that.
So we need to figure out how to do the batched mul here, because clearly I'm not getting something. So if we do so how do we do a T by T by a B by T by C to get a B by T by C? How do we do this in Julia? So X is this, and then Y. So this should work, right? And then we have to do a stack to get an 8 by 4 by 8 by 2. Cool. So this gives us that. But we need to TensorCast. Ooh. Nice. Oh, cool. They have an infix for it. What's the infix character? Box times. Wait, so let's see. Dude, that's sick. Learning something new. Box times. So way. It's weird that it's the other way around, but we still get a 4 by 8 by 2. I feel like I want to check. Let's batch to adjoint. Okay, so this is a 2 by 5 by 17. So wait, this should be. I don't understand that at all. What is going on here? Oh, here we go. Wait, but um when A is a matrix. But we want it the other way around, right? Is this the same? I don't think this is the same. Because way is a matrix. But this is definitely a 4 by 8 by 2. I just don't know if it's right. So wait, can we do it with more non-float numbers then? So let's do it small. Make it 2 by or yeah, 4 by 3 by 2. Okay, then okay. So then wait, is this tiny little matrix? You can comment this out. A1 has size C1. I don't know what does that mean? So this is supposed to be a fast weighted average. I feel like I should just write it like this, but the thing is this is not batched. That is true. It's not batched. But I've lost so much information. Like I don't really understand. So this is 4. So wait, let's just take the first one. So this is or wait. So we have C and let's just do 1 1. Okay, so we have a 3 by 2. So what was X again? Wait, no, wait. X? What is X? No. We want X to be. Oops. I think we need to do this, right? What? What? Oh, wait, why didn't... That's literally the same method, I swear to God. Oh, no, I'm stupid. You can't name it C, bruh. C matrix. Okay. All right. Oh, wait, but that's the wrong one. Yeah, that's the one that fails. Okay, wait, so what is X? Okay, so let me think about this. The time is 3, so that's this. And then 2 is the embedding dimension. So the embedding for the first character, just like what we said, is this. 8 and 10, right? Okay, so that's the embedding for the first character. So now we want to, so now the second, but we want the second character. Let's do the second character. Because the second character should be 9 and 6. So this is going to be 2. And again, this is just the first batch. Wait, 4 and 3. Wait, that's then what is this 4 here? The 4 is the 4 is the, wait, so what is x1? This is a 3 by 2, right? Okay, yes. So this is 4 and 3. Okay. So the second character is embedding. So what we should get is we should get is 6 and 6.5, I guess, because that's the average. Seems wrong. Let's see. This we know to be correct, right? Eight, 10, 6, 6.5. Yeah, so that's right. Oh, wait, here. Wait, is it, no, is that result? That's result. What is CM? This batched mole is no good. Whatever. Should we just continue? And I have to take a break here because the gardeners are here. Bro, there's so much noise in the streets, and it's evil, man. We have got to get rid of the noise. It's so fucking bad. It's actually such a travesty. There's construction, there's leaf blowers just constantly. It's evil. We need to bring back peace. All right, so that's what we want. And I'm just going to leave it like that. We can figure out all this batch to mole stuff later. Because in our case, A is a matrix. So this is the one that we want. So, okay, so 16 by 8. Okay, whatever. We found a solution. It's just slow. Okay. Okay, I gotta take a leak. I'll be back. We have our data set, though. It's pretty hype. I kind of wanted to train it on MLP, but I feel like we should just get attention now because that's the whole insight. That's the thing that's launched this whole paradigm of LLMs is the transformer. So that's the what is batch to multiply? Torch-liked batched mole. Okay, whatever. Okay.
So basically, I want to discuss that.
Yeah, dude, I really want to figure out this batched mole thing. $16 by 8. by do we have this? Is Tensor Core already a dep? Okay, wait. Julia's arrays are column major, thus it usually makes sense to regard the last as the batch. Oh, this is very helpful. Okay, so wait. Can we try that? Okay, so let's say that we got the batch in the last one. So what do we have? We have x and we have y. Y has no batch dimension. Let's permute dims. So x b is equal to permute dims x 2 by 3 by 1. Didn't we do this already? Anyways, let's try it. So y times x. Oh wait, xb. Fuck yeah. Okay, so that's what we want. And let's just check it because all right, so then cm11 or cm1 is 2 by oh wait, hold on. 8 and 10, 6. Okay, so cool. So we figured it out. Thank God, dude. I was getting tweaked the hell out. Somehow I was on the right track, though. I was bumbling around. Okay, so wait. Can we do a B time? .6 microseconds. 30 allocations. That's probably a bad boy. Bad boy. Wait, what happened? Oh, I fucked it up. So it's like twice as fast. Wait, but why does it have 50 allocations? That's insane, dude. Okay, wait, let's pre-allocate. Let's just pre-allocate. B by T by C, right? Oh, wait, no. T by C by B. And then this is way and this is XB. What? Okay, so I guess it's got to allocate. How do we fucking do this shit then? All right, whatever. We found that we found this semi-fast one. I'm good, bro. So whatever. I'm good. This is what we use for the batch to mull. Okay. Finally, we can move on.
And the weights are specified in this T by T array. And we're basically doing weighted sums. And these weighted sums are according to the weights inside here, they take on sort of this triangular form. And so that means that the token at the fifth dimension will only get information from the tokens received. So that's exactly what we want. And finally, I would like to rewrite it in one way, and we're going to see why that's useful. So this is the third line, and it's also identical to the first and second. But let me talk through it. It uses some math. So trill here is this matrix, little triangular ones. Weight against is all zero. Okay, so if I just print weight here, it's all zero. Then I use masked fill. So what this is doing is weight dot masked fill, it's all zeros. And I'm saying for all the elements where trill is equal to zero, make them be negative 50. So all the elements where trill is zero will become negative 50 now.
But why, bro? Because it sums and divides. It's just such a goofy thing, bro. I'm declaring that goofy bro. But I think it's a performance thing. That's it. I just think it's a performance thing.
Now the reason that this is a bit more interesting, and the reason we're going to end up using it in Software is that
Can we softmax along a dimension? What's way? Way is nice. Okay.
quick preview is that
But wait, did we
affinities between the tokens are not going to be discovered at zero. They're going to be
Hold on. What?
Embedding table. So self-acquisition embedding table is an embedding of block size by an embedding. And so each position from 0 that segments 1 will also get its own embedding. By T for and in here we're also going to have pulse embedding, which is the positional embedding. And all those integers, 0 to T minus 1, get embedded through the table between T by C.
It's the sum of the token embedding and the position embedding. Now that's an interesting thing. Why would you do that? All right, so let's get up to speed to where he's at. So what is all this? This is a bunch of garbage. This is just showing that the structure of whatever. Okay. So so let's get vocab size. I guess we want to keep to the names. We're gonna keep using names as our data set because it's just it's just useful. So below the functions, do this. Okay, so so the embedding, so there's character embeddings. Oh yeah, and so n embed. Let's make it 2 for right now. So this is going to be vocab size and embed, and this is going to be the token embedding. Then we have the POS embedding, which is an embedding, and we're going to make a new thing, which is the POS MDIM, right? No. Well, okay, he keeps it the same. But yeah, so the position embedding has to be block size, and block size we can define down here to an embed. Okay. Oh, but does it have to be the same? I guess it does have to be the same because we are. Excuse me. Um. Let's just get a how do you do this? How do you? I wish it had the keyboard shortcuts there. Okay. Oh, did it work? Okay. T is 8. Oh, he's using 8. We're using 3. This should just be 1, 2, 3, right? What are his imports? Can we go to this code just to look at the imports? And this is going to be 3 by 2. Interesting. So PE of 1. Wait, what? Oh my god, dude, that is crazy. That is crazy, bro. You gotta literally do torch.tensor of 1. That's crazy that you gotta write that shit out. You can't just use 1. Whatever. Anyway, so it's like a weirdly 1-indexed thing. So it's like a 1 indexed into a 0 index. What happens if you give it 0? I'm curious. It errors, right? Oh, no, it doesn't error. Wait, so then what is A range? A range starts at 0 then? Okay. So then what is range? Okay. All right, there's just a bunch of quirks. That's fine. I'm not going to get too stressed about it. Because we're trying to learn AI, bro. We're trying to learn AI. Oh, I never turned off that hose, probably. Okay, I'm gonna take another leak. Should get some water, actually. Okay. Wait, can we look at XB? Okay, so XB is T by C by, and C is this, right? What did he say? He said there was a weird thing there, right? Is that oh, interesting. Okay, wait. So, all right, so we'll get to that. But a thing that I wanted to know was okay. So wait, let's just try to get a grasp on this column major thing. So m is equal to rand 5 by 10. So we have 5 down and 10 across. Okay, now if we do m1, we get 8. Okay, but now if we get m2, we go down, right? We get 0.84. We don't go across. But let's just see if we can get a m is equal to torch.rand 5 by 10. Oh, I hate this thing. Why doesn't it show it like a matrix? It's so stupid. Anyways, but you can clearly see that it's row major because it's like a list of rows, not a list of columns. Anyways, so that's like the fundamental challenge if you're trying to write Julia neural net code is you got to get used to the fact that the language is column major. And so what does that mean in terms of multi-dimensional arrays, I guess is a question. Because let's say you have a 5 by 10 by 2 now. Okay. So M2 is going to be what? 0.097. It's going to be here. So then if we do, so 5 times 10 is 50. If we do 51, we're going to get 6.5. Okay. I don't really get why it being column major means you have to do the permute dims. But in any case, I feel like I have enough of a grasp on it. This is just column major stuff. We can just comment this out. Okay. Batched mul works when the batch is the last dimension. Okay, cool. Nice. And then figure out how to make batched mul work too for speed. Okay. The thing is, I feel like by doing, oh, he's not there yet, but by doing that mul, Torch is also allocating. Anyways, okay, so index, so this is a batch. So wait, what goes into this? Oh, a batch by time. A B by T. Yeah, so you get 4 examples. Okay, cool. So, so in our case, let's just build the data set again. So I think we have X, right? Oh, this is the wrong X. XS. Okay, so this is the big thing, X's. So we want to get a... let's get a batch. I think we have a batch, right? Okay, so we have a batch. So what we want to do, so this is so T is 3. Yeah, so T is 3, B is 32. Let's actually get a batch size of 4. And then we'll do this. Okay, so now we have a 4 by 3. So we have a B by T. And okay, so B by T. okay, so the let's do this. Emb layer. So, and this is going to be the whole index. It's going to be, it's going to take a whole batch. It's going to be a 2 by 4 by 3. I don't know about that. And this is going to be just T. Wait, T? No, a range of T, right. So, wait, what is the type of this? It's a unit range, but there's base.1, 2. So this is going to be n embed by 3, right? Which is T. And this is going to be 2 by n embed by B by T. Wait, by T? No, by C, right? Wait, 2. Oh, this is C. Wait, C? That's C. But that's a different C, I guess, is what the point was. Token. No, that's C. But it's goofy that it's so. I think it's because. Okay, wait. I think it's because. So batch is 4 by 3. That's 2 by 3 by 4, which is C by T by B. Okay, let's just get one thing at a time. Because I'm pretty sure that if I just... Because token emble... I mean, it's literally just a lookup. We can just give it 1, and it gives me a length 2 vector, right? But if I give it 28, it errors. But so it's literally just a lookup. So if we just do dot batch, what does it give me? Yeah, right. Exactly. Because batch is a 4 by 3. So if we wanted a 4 by 3 by 2, yeah, okay. Just remember, embedding is literally just a lookup. So this is just reminder that embedding is literally just a lookup, like a performant. All right. So, but we do need it to be the correct. I wonder if we can do what does stack give? Stack gives a 2 by 4 by 3. Okay, so it literally is just calling a stack then, basically. So we get a C by B by T. But C is equal to C, right? I don't know. I'll have to keep going. So, all right. So what is the next step for the forward passes? We need a dense layer from the embedding dimension to the vocab size. Okay, so then we need LM head, which is dense from the n embed to vocab size. Okay, cool. So now we should be able to do... So the interesting thing is going to be whether or not... is basically how we get the position embedding and the token embedding to add together. So we have toke emb. which is 2 by 4 by 3. So can we remember how to do a batched add? Does nnlib have a batched add, actually? No. Okay, so wait. Let's just figure this out. I know I've done this before, but getting these shapes right is so crazy. Honestly, I'd rather be in shape hell than in file system hell, where I'm just constantly having to write file paths all day. So if we have a rand 5 by 10, so this is M. Let's just intermediate forward pass of self-attention. Okay, so I can delete this now. If we have a 5 by 10, and we have a B, which is 1 by 10, or just rand 10, and we do M dot plus B, does that work out? Because the thing is, I think it's because Julia wants to add along columns. So it's not left aligning, or it's not right aligning the dimensions, it's left aligning the dimensions. I think that's, okay, so Julia is left aligning dimensions as its broadcast rule. I think that's what's happening, because if we do 10 by 5 and then we do M dot plus B, then it works out. So maybe that's the secret to everything, is that we left align and then we add dimensions if we need to. So in that case, we have, what? Did I fucking rewrite T? What? Oh. Okay, so we have a 2 by 3. So what we want to do is we want to permute dims. So wait, so let's just verify that pos, so in what order does he do it? It shouldn't matter because it's commutative. So token m plus pos m. So this fails. And then broadcasted also fails. So what we want to try is now throws. So what we want to try now is a permute dims of this, where it's so toke emb is, which means this is 2 by 4 by 3, right? So toke emb 2 by 4 by 3. So what we want to permute this to is 2 by 3 by 4. So we want to go, right? Because pos emb is 2 by 3. So we want to go 1, 3, 2. And there we go. Nice. Good stuff. So this is X. And then we can just call logits is equal to, so maybe we do want to add some of this training code now. Now that we have some of this vague. So now, but what is it that we've actually done? We've basically created a positional embedding so that if E, so the fact that E is in the second character is somehow differently significant than if it's in the first, which seems odd. I'm going to be honest. So this now means that an E at pos2 will have a different overall embedding, meaning as an input, than if it were in a different position. So now, what I'm curious about is what do the positional embeddings look like? Because like, of what significance is it? Who's to care whether or not E is in position 2 or not? I don't know. Seems a little bit interesting. But look, it works, so you can't freaking knock it. So anyways, this is going to be LM head of X. And presumably this is a batched mole. But wait, but I feel like what's interesting about this is that in here, my model, maybe it does some fanciness to figure out which one's the batch dimension. (27 by 3 by 4). 27 by 3 by 4 sounds wrong, right? Because we're getting V by T by B. V by... So this at the end should go... okay, I guess that's right. V, B, T. Okay, so let's keep going. So no head. Do we want to write that code? I feel like I could hold off. All right, let's just do it so that you guys know that I ain't no bitch. So let's write it up here. So the other way to do this, so let's just say we got bit trill of T by T. Okay, it's gonna be A, and then we want to do fill. Wait, how did we do this? I feel like I did this. Oh, I deleted the code. Let me go to my code base. Here. It was in not attention but MLP clean, and is at the bottom. How did we? No. How did we? I guess I deleted it, but I'm pretty sure it was in the last one. But basically, what we want to do is set all of these indices. So we want to dot not this. So we want to take, where's A? So we want to do dot not A. So that gives us the inversion. And honestly, there's probably instead of a trill, there's probably a try-u. Is there not? There is a try-u. So we can do a bit try-u. Anyways, so we got this. I'm going to do M equals zeros T by T. And then we do M of these indices dot equals minus inf. So then now if we look at M, we have exactly what he was saying. But now we want to do a soft max of this. So we want to do soft max of M, and let's see if that's right. And that is wrong. So now we have to do dims equals 2. And there we go. So now we have this. So this would be CM. Oops. Okay, so that's just like the other way, I guess, to do this weighted matrix thing. I don't actually know why you need to do the softmax. It seems like it's like strictly slower, but I guess that's the way to do it.
So when we initialize the affinity, we know the different tokens to be 0, then we see that weight gives us this structure where every single row has these uniform numbers. And so that's what then is matrix multiplied
Yep.
makes sense of what we're doing. Because different tokens will find different other tokens more or less interesting, and we want that to be data dependent. So for example, if I'm a vowel, then maybe I'm looking for consonants in my past, and maybe I want to know what those consonants are, and I want that information to flow to me. And so I want to now gather information from the past, but I want to do it in a data dependent way. And this is the problem that self-attention solves.
Okay, wait. Let's. Okay, I know you guys can't hear what he's saying, but that's intentional. That's for the purity of my transcript. But we don't want it to be uniform. Different tokens will find other tokens more or less interesting,
Or less interesting, and we want that to be data dependent.
and that's data dependent.
Then maybe I'm looking for consonants in my past.
If I'm a vowel, then maybe I'm looking for consonants in my past. If I'm a vowel, then I want to look for consonants. Okay. Okay. Every single token will emit a query and a key. The query is what am I looking for? And what do I contain is the key. Yeah, I mean, it's very interesting that such a system has become so successful because it's really not that complicated, and it doesn't seem like it's surprisingly simple. That is sort of the biggest thing I feel like I've gained is that self-attention is not all that special in terms of like it's just allowing. It's just an operator that really allows contextual dependency. Oh, so a single head. Okay, so we have okay head size equals and I want to keep it small. I want to keep it like 6 or something. I want it to be a unique dimension, but I want it to be as small as possible. Okay, so now what we're going to do is, so for a single head, we have a key, and this is going to be a dense from vocab size or an embed? From C. C to head size. Oh, bias equals false. And then a query. This is the same thing. And so what we're saying is that so it takes a C, not a T, a C. It takes a C and it takes a single C though. That's the interesting part. It takes a single C. Wait, so what is the size of this matrix? It's 6 by 2. Head size by embedding dimension. So now we can multiply this by something embedding. So we could do times, and this is going to be something that's 2 by something. Okay. on X. So let's remember what X is. Okay. So these are both going to be 6 by both head size by C by B.
So the size of this will now become
Oh wait. Yeah. T. Okay, right. So what we're saying here is that we're getting. So okay, wait. Let's look at K. So K is 6 by 3 by 4. So let's just look at. Just assume that the batch size was 1. So we'll do this. The batch size was 1, so we get a 6 by 3 matrix. So originally, we had a 2-dimensional embedding for a thing, but now we've expanded it out so that we have, for each character, we have 6 numbers. For each character in X, we have 6 numbers. That describe what oh wait, I forgot to do this. I have to do this down here. Wait, but did he do this out? No, this is still up here. So X is okay. Okay, so K and Q are the same size. But what do we want out of it? We want a Q times K. Okay, so let's just say we have a 4 by 3 by 16. So let's go to this. So we have K is equal to torch dot rand. And then can I do just range 1 to 10? Let's see, does this work? Oh my fucking god. How the fuck do you how the fuck did he do this? Python is so absurd. Where did he do that thing? No, this is all the bigram stuff. There we go. So he did rand int. Okay. 110 by 5, and I believe this also fails, but I'm pretty sure it's because you need this. Okay, there you go. So now I love that it just doesn't show you the value. It's so stupid. Why not just show me what it is? Because then I have to constantly. Okay, so we want a B by T by N head. So we want a 4 by T by N head, which is 6. So this is the K, and then this is the Q. It's the same thing. So let's just duplicate this and make this Q, and then delete this. All right, so now we have this. So now it's Q at K dot transpose, and it needs a dimension. So let's go back there.
Yeah, so we can transpose.
Okay, there you go. B by T by T. B by T by T. Okay. So we want a B by T by T. So if we permute, so it's gonna be 6 by 3 by 4. So 6 by 3. So I'm pretty sure we want to transpose this one. So we get a 3 by, so we want to permute dims, and this is gonna be this. 2, 1, 3. It's not gonna be this. It's gonna be this box. What the hell is it called, bro? What is this? What the hell? Great for not. Thank you for not telling me the name of it. Box times. There we go. Okay, so that's what we have to do. We have to permute it like that. Does this actually allocate? Can we do a B time on permute dims? Oh wait, can we get a shape? It probably allocate. Yeah, all it does. Oh, this is fast. So all it allocates is that. So I'm sure if we did this, we said, we did it again. It still has an allocation. I don't know. I guess the result. Anyways, so now we get our T by T by B. Because if we were to do this, Q box times permute dims, and then we did this as dims, we get a 6 by 6, which is wrong. Okay. What I'm wondering is, has anyone thought about putting a nonlinearity after the head or after the key and query? Start to really sort what you are looking for. I don't know. Okay, wait. So out. So wait. Hold on. So we get the way. And then okay, so we got the way. So okay, so this is not out, but it's way. This is way. So now we want to go get the other way stuff. So what is M? No, we want to do way. So we got this way. Wait. But the thing is trill, but way is oh geez. Okay, so we gotta. I think you can map along a dimension. Map dims. Map. Hmm. It's already 2 p.m., bro. Okay. Um. Wait. So, oops. So we have way. We're trying to do. Okay. Wait. I think I can do this hella quickly. So this fails, right? But what we want to do is across. Oh, that's so fucking sick. But I think it's wrong. Oh no, it's not, dude. Oh, that's so concise. That's so clean. So wait, so we got way. And then what we want to do is soft max across the second dimension. Did I fuck it up? Let's look at CM. I don't know. I guess there is a linearity. Softmax is nonlinear, right? Or is softmax nonlinear? So out is way times x. Where is x? Oh, that's interesting. Wait, way is. So this is way. So let's keep it as CM. CM times x. We need to do a batched mole, right? Because x is b by t by c. CM is t by t by b. So we're trying to do a BTT times a BTC. So what we actually, but wait, is that right or no? This is a t by t by b, and this is a 2 by 3 by 4. This is a C by T by B. But didn't we do a permute on... So I think what I have to do is just permute, and this needs to be a 2, 1, 3, and then this needs to be a box times. And then we get a 3 by 2 by 4, which is a... to get a... So we need a T by C. Goes to... T by C by B. Cool. Oh. And that is out. Are you recording? Jesus. All right. Okay. So what actually is way 0? Okay, so way is the affinities. Way is the alignment of the K's and the Q's, the keys and the queries. Is Sora out? Damn, bro. Account creation currently unavailable. Shit is so annoying, bro. They said Sora's out. Yeah. Right. Sora's out. Dude, there's a house like like right down there, and they've been using a jackhammer for like 2 days straight, bro. There's just too much construction going on. I mean, Ebby is literally just a jackhammer. It's like someone left it on. So absurd. All right. Oh, fuck. The fucking lawnmowers, bruh. Whatever, I don't give a fuck. Uh, Wait, why did they have to do value? Oh. Nice. Wait, 3x6? Hold on. I think that's wrong. The Let me go for a walk. These gardeners, bro, it's just a waste. Okay, what I'm thinking is we got to just get rid of the batch dimension. What is the point of doing this starting out with the batch dimension? It doesn't make sense. We're going to start all over. We're going to start all over. Okay, so that's X. The next thing we need to do is make a way. Right. And what are we trying to do? We are trying to multiply y times x. And then we get, wait, what? Wait, what? There we go. Yeah. So 1.0, 1, 6. So wait, so we take x, and we take y times x. Three, 5. Okay, there you go. Okay, so now that's that. So the next step is, see how much of this code that we can get rid of? It's like, if you just get rid of the batch. And then similarly, let's do this with, oh, well, that's the same. Okay, all of these are the same, so we can still use all of these. So we have a batch, right? That's that. X. X is like a... X is not a batch. X is X is T by C. T by C. So this is going to be the same. Token embedding layer goes from vocab size to an embed. But you can just give it a vector, right? Like you can give it a random vector. Wait, but that's not what we want, right? Like this is a T by C, which means that for each of these three characters, we got two numbers that represent its embedding. So anyways, if we go token, and we do this of x, 2 by 3 by 2. No, but see, that's not what we want. Fuck it. We'll do the, it's added to do start from scratch with no batching. No batching. Because then I feel like all these shapes will make more sense. See, the problem here is, dude, this is so insane, man. I walked over to these neighbors, and I was like, oh, thank God that staircase is done being crumpled by their fucking jackhammers. Nah, they got a whole nother stair left. It's crazy shit, man. It's like, that can't be the most efficient way to break up that rock. And imagine listening to a jackhammer for 8 hours, bro. It sucks. Okay. So here's the problem: is V. Wait. So let's copy this code. Let's get the collab. But it's all written like this. It's all written so annoyingly. That's the bigram. Here we go. This is what we want. V is, so in his case, it's, let's just make him R shapes so that we're good. So B is 4, T is 3, and C is 2. V is 4 by 3 by 16. In our case, I need to get some water. I don't get how the value works out. Because if you have a... Wait, what is the shape of this? V dot shape... Oh no, so out dot shape is not B by T by C. Okay, out. Yo, what's up, NR? What's going on? Yeah, the out shape is not B by T by C. Okay, that's fine then. But we just have to make the mole work. So out, does this work though? Yeah, so this is T by H by B. Okay, cool. So this is fine. This out is correct. And then we do logits. The problem is LM head is a dense of what? N embed, which is 2. But this doesn't work, right? Or wait. This doesn't work? Yeah, so this doesn't work. Size input of 1 is equal to 2. So wait, did he change the LM head? Where is that? Oh, no, he hasn't done that yet. From now, I only have 0 skills of training in AI. I'm here to see how it works. Only basics. All right, so let's go through what we did, because it's always good to start from ground zero. So I also have I would say pretty shallow understanding of AI. So let's go to okay, I'll just explain the general overview of this series by Andrej. So there's a series, Neural Networks Zero to Hero, and it's basically start to finish, going from the beginnings, starting history of language modeling, all the way up to the present day, which is GPT style large language models. And the first thing that you start out with is, let's say that we want to make something that can generate text. Well, one way that you might do that, let's say you have a corpus of text, like a whole bunch of just like Shakespeare or something. Or in our case, we have this data set. Oh, wait, what is it called? Okay, we have this big string, okay? And what we want to do is we want to take one character and predict the next. So what we could do is we could zip these together. We could take T and T from 2 to the end. And so now we have all of the pairs of characters. So we have basically, okay, wait, let's so let's do this. We have all the pairs of characters. So what this is like, let's take first of PS, and this is Y to O. So basically what we're going to do is we're going to tally up. So what we could do is we could now tally PS. And what we could see is that the most common character that comes after E is a space, and the most common character that comes after a space is T. So what we could do is we could take this and turn this into a probability vector. So anytime you see an E, there's some probability associated with the next thing. So if we were to take the unique values of T, then we get our alphabet, and we'd sort this. Okay, so now we have an alphabet, and this includes all sorts of weird characters in it, like a squared symbol. Anyway, so this is what's called bigram language modeling, okay? This is the idea that you basically are using only one state to predict the next. And the problem with this is that it ends up generating really crap code, really crap language. Like, it doesn't produce anything sensical. So first off, let's just say the alphabet is this. And then we what we want to do is we want to create what we want to do is we want to create the product of this. So iter product. Can we do this of alpha and alpha? And let's collect this. All right, so now we have a matrix, right? So let's make a vec of this. So now we have a vector of all of these pairs. And so what we want to do is for for x in the tally, what we want to do is we want to make a dict of these. So we want to make this dot to 0. All right, so now we have a dict where we have 2 characters, and it's basically every pair of character. It's every pair of character, and it goes to 0. And then for x in tally, what we're going to do is we're going to say, so this is going to be d, and we're going to go d of x plus equals 1. Okay? And it didn't find this key, which makes no sense because, so wait, hold on. Let's say alpha is 87. 87 squared is, so that seems interesting. Wait, so let's do d of e. So then space, oh, what? Wait, first of, let's just say the tal is this. Okay, you want to know how the neural network works? All right, I'll tell you that. We'll get on to it. Get on with it! Anyways, so the next thing that you do is you expand this data set. So you start now with a bigger context size. So now you're going to say, I'm going to look at the next 3 characters, but instead of using this counting model, this bigram counting model, we're going to use a neural network to learn basically an estimate of the probability that the next character is something, and then you draw from that. So the neural network looks like this. So basically and this is called a multi-layer perceptron model. And basically the high level of how it works is that for each character you have some embedding. So you have some way to represent and learn a sequence of numbers that represents a character, or in the case of big AIs, a token. But in our case, we're just doing letters. And then what you do from there is you multiply it through a neural network layer, which is basically just a matrix multiplication, a bias, and then a nonlinearity. And then after that nonlinearity, you project it back down to a size of vocab size. So the output of a model, so let's just say, I don't know if this is still right. Is this all going to be ones? I think this is going to be good. So if we do model of x, little x, what we're going to get out is a bunch of probabilities of the next character. These aren't strictly probabilities because you need to actually softmax them. So if we do softmax of model, then I believe, so it's 27 by 32. So let's just say this is the softmax. If we take the first column here and we sum this up, we should get 1. So that means we could draw from this. We could sample this to figure out what a predicted next token is. Does that make sense? So then the way that we learn, this is sort of the way that we learn. And I'm not going to go through how to make an automatic differentiation engine because I don't have that here and it's going to take too long. I have been meaning to write that, honestly. But this is basically the whole code that it takes to train the neural network. And it's honestly could be less than this if I cleaned it up a little bit. But basically, this is the most important loop. So we have a bunch of data. So let's look at loader. So we're going to take the first batch. So wait, we don't want the first batch. What we want is this and this. Okay, so we have a batch, and then we have a Y1. And what we're doing here is we are saying that, so let's just say, so what we're trying to do is we're trying to predict, I believe I can do, ooh, I wonder if this will work. Oh, hell yeah, that's so sick, dude. I'm fucking awesome. GetD is such a sick function. So, okay, so what we're doing is for each column here, we're saying, okay, .al is supposed to predict, it's supposed to predict L after this. And then for .m, you're supposed to predict an I. And so from these little batches, you get a bunch of logits. So let's do this. Oh, x batch is equal to batch. And then we can do this, and m is equal to model. I actually don't know why we have to do that. And in any case, wait, but I don't think we need, no. Hold on. Give me 1 second. All right. So these are the logits. So these are those probabilities that we looked at. And then what we do is we take a loss value, which is basically what is the correct, so wait, y batch equals y1. We can do this. And so then we compute a loss value, which is basically how wrong was the neural network at predicting. So, the crux of machine learning in neural networks is basically answering the question of like, okay, I have this big function. I have this huge mathematical expression. It can be small, it can be big, but in modern AI, it's big. And then we have to have a way of computing using the chain rule from calculus. How do we compute a number that represents how incorrect our function, this big composed function, is at recreating or doing some task. And so that's called the loss. So this is the loss, and basically the whole code is couched in this flux with gradient function. And with gradient, it basically does this recursive chain rule to figure out, with respect to the parameters of a model, how do we increase, how do we decrease the loss so that it approaches zero, so that the model is as correct as possible. So that's what we're doing. So this is like the most simple neural network model for language modeling. We are now going to attention based modeling, which is what all GPTs are based on, and what basically most of the AI hype is based around is this attention mechanism. So we're just going through the lecture right now.
And this is done in a data-dependent manner, so depending on whatever data is actually stored, it shows at any point in time. Now, our graph doesn't look like this. Our graph has a different structure. We have 8 nodes because the block size is 8, and there's always 8 tokens. And the first node is only pointed to by itself. The second node is pointed to by the first node and itself, all the way up to the 8th node, which is pointed to by all the previous nodes and itself. And so that's the structure that our directed graph has, or happens to have, in autoregressive sort of scenario like language modeling. But in principle, attention can be applied to any arbitrary directed graph, and it's just a communication mechanism between the nodes. The second node is that notice that there's no notion of space. So attention simply acts over like the set of vectors in this graph. And so by default, these nodes have no idea where they are positioned in space. And that's why we need to encode the position and sort of give them some information that's anchored to a specific position so that they.
Yeah, I mean, it makes sense that you need a position vector. It just okay, wait. Like if you said to it hello. So no. So so that there's a step after training this. So the first step of training an AI like that is you train it to predict text. But after that, you start to fine tune it so that it acts like a chatbot. And that's done with reinforcement learning and other mechanisms, fine tuning. But the big model, the important part of the model is the prediction engine. But on top of that is layered subsequent steps where it acts like a chatbot. So no, the result of any of these language models would not be a chatbot. You would have to do extra work on top of it. Oh, and by the way, bro, I'm training an AI on the transcripts of my live streams. Why doesn't that work? Oh, wait. Cool. Let's fucking I'm just curious. Let's go back to the bigram stuff. Read, and then we need the path of this thing. Copy path. So now what we want is to make a matrix of this, right? So wait, hold on. Does this return a matrix? Oops. Right. So then what we want to do is a get D. So this is the So what we want to do now is get D keyem. And then we get a matrix, and then we can do a heat map of this. Wait. Why is it not doing a plus equals? Oh, wait, because we're doing it on the tally. I'm stupid as hell. Not the tally, it's the P's. But look at this. A bunch don't show up. That's interesting, right? Oh, okay, wait. Now we can do it as X. Okay. Wow, it's super diffuse. It is super, super diffuse. So what we could do here is regularize it. Look at these counts. What is the, can we look at the key M? New line to new line. Somewhat common. New line to space, somewhat common. There's a whole bunch of random characters in here. I wonder what those are. So the new line's the first guy, then the space, then the hash, then the dollar sign. I don't know how the dollar sign, I guess the transcript, if I say like $50, it's gonna, so what we want to do is we want to, how was it? How was it? If we, so we have this matrix, and what we want to do is so first off, so now there's no non-zeros. Okay, we can do a heat. Okay, and then what we want to do is, for R, we want to, for each of these, we want to predict, so for each row, let's just, let's write this norm rows function. Let's just norm the rows. Norm rows of R. R is equal to this. Okay, so now what we want to do is sample. How does sample work? Or actually, I think we can sample without normalizing. So let's say the start is a new line. We'll just say the start is a new line. Oh, we need to make the I2S and everything. I don't know if I want to do I2S. I guess we could. So it takes an alpha and then it makes an I2S and an S2I. Okay. Okay, so we can take this and copy this over here. So the X map, so we get the okay, nice. So now we have this. So what we want to do is we want to start off with 1. So I2S of 1 is a new line. So we get an I2S. So it's going to be sample R of I2S of 1, or of x. We're going to say x equals 1. X, like that. Oh, wait. S to I. Wait, no. Or this is going to be... Okay, cool. So then... So let's just say x equals 1. Okay, so instead of doing S2I this, we can just do x, and we sample this, and then we push onto the gen the I2S of x. And then, so x equals 1, gen equals nothing. Key 116 is not found. Is that because... Wait, but this is the counts. That's not what we're looking for. Wait, we are trying to sample from that. But we're trying to sample the... We're trying to get the index of that, though. So how do we do that? Can we go back to our bigram generation code? Wait, this is the neural net, but where's the... Yeah, because we need to get the index. So we start here, or we start here at the new line character, and then we sample here, and that gives us a number there, right? Wait, but how does sample work? Oh wait, why don't we do this? One, two of I think that this will work then. Wait. This, what does this return then? Abstract weights? Select a... I think what we want to do... Wait. What? What is abstract weights? Okay. Oh. That's funny though. That's their bigram model. That's a bigram character model, bruh. Corin Aldong Nuris. Or wait, no, Urus Batonged Thayatet Kangon Donks. No. No, let's make a bunch of this shit. Wow. I mean, it looks kind of 3D Dofol. Hello. Wires Frathel Vigo Vi. Acus Cameños. O Ayo tentame walco. Go uplo yo me. Oh, allo. This is fucking awesome, bro. I can't wait to train this and see this get better, bro. Allo. Wesoli rung. Tilidole tavem ta ohe. Auhe. Al honorete hare kuta rita musol mister. Wide eye. Kathala clot tathasa. Very interesting. Oh, and it's so interesting. Look at that. Because music occurs so many times that after C, it puts a freaking. Oh, man. I mean, bigram models, like, after seeing this, it's like the structure is there, though. Like, there's a lot of structure just between two characters. I should probably go study for my final. What time is it? 3. Oh. Ay, ay, ay. Dude, I got 20 people in my Discord community right now. I'm so sick. All right, it's actually 19. It's actually a 19. Okay, so but the thing is, you don't want to build the full data set. Now you want to sample indices. So maybe we should just start from scratch. I mean, we just built a bigram model in like 5 seconds. Pretty sweet. And the thing that's cool about this is well, yeah, so the weakness of it for sure is let's see what happens if we don't regularize it. And also the start char yeah, oh bum. So actually smoothing it out. Besen cooking. Offerv. Offeriv. Then canker I've the levum. Oh hermome. Dude, it's so sick how easy it is to make a bigram model. That's the thing. Is like to go any further, it takes so much more. But the bigram model just works like so simply. Obviously, it's total garbage, but pretty sick. Let's push this code. All right. I feel like that was pretty good. 4-hour stream. Slamming it. Definitely this ending bigram thing is like nice. Should we try to freaking make an MLP work? All right, we're going to do this hella quickly. I'm going to go to the bathroom and then we're going to just do this. And the thing is, it's actually nice to start from scratch and just do it again because then we'll really know everything. And I'm not going to do a validation and test split. I'm just going to do 2 splits. All right. Hell yeah. So we're going to start from scratch. Okay. No libraries right now. Well, we'll have to use a library, but the point is we're starting from nothing and we're going to train a model on myself. So first off, I'm going to try to not refer to the code I've already written as much as possible, but I will copy in some functions and stuff like that. Okay, so the first thing we're going to do is we're going to define a function that first what we're going to do is we're going to read in our data set. We have a T, that's our data set, okay? L is going to be length of T, okay? So that's the length of T. Now what we want to do is define a block size to be 3, okay? So then what we also want to do is int of 0.9 times L, round, okay? I guess, round to int, okay? So this is the index of the train test split index is equal to this. So what we want to do is let's first build the index maps. So we want to get the sort of the unique of T. So this is the C's, okay? But then what we want to do is we want to find a character not in this list. So what we want to do, let's find like a, is a semicolon. Okay, so semicolon is not in it. So semicolon is going to be our pad character. So this is semi is pad char. So what we're going to do is chars is equal to semicolon C's. Okay, so now we have 88. Now what we're going to do is say S2I, I2S is equal to X maps of chars. So now we have these two dictionaries. Okay, and what we can do is we can encode and decode strings with them. So we could do get D, I2S of, S2I of a string, right? Which would be, or collect of T. So this would give us a vector of all of the integers. So we now encoded the entire data set. But we don't really need to do that. That's just to show, and what we could do here is we could do get D of I to S of this, and then we get them all back, and we could just join them, and we could test that they're equal to T. And this is true. So we have encoded and decoded the string back and forth. So this is showing how that works. So now what do we need to do is we need to set up the model, really. But first I feel like we should start with getting a batch. So let's just say the batch size is equal to 32. So what we want to do is we want to get a random we want to get 32 or batch size number of random indices between 1 and split index minus batch size. Because, or not batch size, block size. Because block size is the number of characters we're using to predict. So if we go to the end, then we're going to go over, which is not good. And then we want to get batch size number of these. So these are going to be, oh, and one thing that we want to do is we kind of want to shuffle. But how do you shuffle? In this case, I'm not going to shuffle, but in practice, you really need to shuffle. So these are going to be the okay, so these are the X indices. So what we want to do to get a batch is these are the start indices. So what we're going to do is we're going to take map X to X, or wait, not X, but T of X to X plus, wait, hold on. So let's just say X is, IX is equal to XIX is 1. So then if we do T of X to X plus block size, then we get 4. So we need to do block size minus 1. And then we get the 3. So this is what we need to do. So T, and this is going to be X, and this is going to be XIXs. So now we have the strings, and now we need to, but what we want to do is, this is a string. We need to get D of I to S. And actually, what happens if we do get D? No, I don't think that. I think I have to call collect of S to I of collect this. So this is the function that creates a batch. Okay, so there's our batch, and now we want to stack this dims equals 1. And now we have a, if I don't do this, this becomes a permuted, right? Which honestly is also fine, but I think it's also fine. But this is the way that I've been doing it thus far. But so now what we need to do is, so, and this is going to take an index. So this is going to be the X batch. And Y batch is going to be well, these are X's. These are X's. So we want to do y, or wait, no, we want to do t of x's dot plus 1, right? Because we're trying to predict the next character. So if we do this, so wait, x's is equal to x's, and we do this, and we get that. Wait, but that's not right. Well, we just need to collect it. And we need to do a, so let's just write a function. Or, wait, do we even need to do this? So we get the next, and then we get d, sti, collect. I think this is what we need to do. So this is the function. So this takes x's, and it returns this. X's. Great. So now this is going to be stir to x's, or whatever. Who cares? Who cares? The name is bad. So now we need to return xb, yb. So if we do, so now we have x's, get batch of x's is, so this is that, and this is that. And so now what we want to do is we want to make our neural network now. We're going to make the neural network. So we're going to now go up here, and we're going to start to use a neural network library. And the first thing we're going to do is we're going to take something like an index into a character. So for each character, we're going to create a string of numbers that can be learned that is a representation of what it means to be an X, or to be, a Y, or to be an A, and so on. So the way that's called is embedding. And what we'll want is an n embed variable, which is we're going to say is 2. And then we're going to also have our vocab size, which is n. So it's going to be mapping nc to nembed, right? So this is the embed layer. Now what we want is e is equal to emb of xb. And so now we get a 2 by 32 by 3. So put the batch dimension in the middle, which is a little bit strange. I wonder if I permute this, what does it do? So that's so we actually do want to, where did we permute it? We did a stack here. I think what we want to do is we want to get rid of that stack. And this goes back to the fundamental difference in Python and Julia. Julia is column major. Anyways, so we're going to get the batch. It's going to be 3 by 32, and this is going to be 32. And this is going to be the embedding, and then we're going to do not that, but this. And so now we get a, so this is going to be C, so this is, let's just call it, well, whatever. C by T, which is block size. And then by batch size, which we'll call B. So this is a C by T by B. Okay. So then the next layer is going to be a, or let's keep that there. The next layer of our neural network is going to be a linear layer. It's going to be a dense. So L1 is going to be called dense. And what do we need? We need the dimension first to be n embed. And then we need it to be a hidden. So this could be anything. So what we're going to say is we're going to say hdim, or nh is equal to, let's just say 100. And so this is going to be n embed to nh. And it doesn't say it here, but I like to be explicit. Let's say, what is the quarg for it? Sigma defaults to identity, which is interesting. Oh, really? Maybe that's why something wasn't working in the past. Anyways, we do sigma equals tan h. How did we do it otherwise? Flux MLP clean. In the creation of the layer, we just say ReLU. So, okay, let's just do that. All right, so we got a tan H layer. All right, so now what are we going to do here? This is a 2 to 100. So if we take the E, which is 2 by 32 by 2 by 3 by 32, and we call L1 on it, we get a 100. So wait, so let's just do the math ourselves so that we can predict it, because otherwise it's silly. So L1 is going to be so L1 has a weight associated to it. So weight is a 100 by 2 matrix. 100 by 2, which is equal to NH by C. Now we're going to be multiplying that with a E, which is, so C is 2, 3, and 32. But the thing is, so we're going to be doing a 100 by 2 times a 2 by 3 by 32. And so we should get, so these are going to collapse, we should get a 100 by 3 by 32. Is that what we got? Okay. So this is the first step. And we can visualize these, but we don't really need to. So then the next step is just to make a second dense layer. And this is just going to have none. And it's going to be from NH to vocab, which is NC. So this is the vocab size. So then we do, so this is LA, and then LB is equal to L2 of LA. All right, so now we have probabilities for each 3 characters. Wait, hold on. Let me get this straight. So we make a chain of that. So we should be able to say model of XB is equal to LB, and that's true. So this is the same thing. But I'm trying to understand. So let's do, so we got the logits. These are the logits. So logits of blank 1. This is going to be an 88 by 3 matrix. But we have not yet sorry, not this. So to compute the loss, right. So this should work. So let's make sure that this works. OP of me. XB, YB. And this is going to be to NC. Yeah, if we run through this, what is the shape of this output? See, so I messed up somewhere. Because we need to collapse that 3. Or no, wait. This, oh wait. Oh yeah, we gotta rename all this. The predictions, for some reason, have this extra dimension there. I think it's the ordering of the... let's run through this again. E. Let's move this down. Oh my gosh. Oh my gosh. Isn't it Shift Tab? Okay. So the embedding, what does the embedding over here look like? Ten by 32 by 3. So what if we go back to the stack? What if we in the get batch? What if in the get batch we add this back? So it's how do you get rid of that third dimension? Oh yeah. No, it's because right, it's because this is not right. Yes. Right. This is going to be n embed times the n embed. N embed times the block size. Right. Yeah, okay. I got it. Okay, we're good. Oops. Yes. Right. So what we want to do is undo this, and we're going to see if we can rewrite this better. So we just get a batch. Okay, and then what we want to do is we want to take a E, and we want to reshape to be blank by batch size, right? So it's going to be E tuple of 6 by 32. So now we should be able to do L1 of this, right? 100 by 32. Okay, cool. So we just need to do this. And I think there's probably like a flatten layer or something. ML utils. Well, in any case, this will work. Fuck. I gotta study, but I'm so interested in neural networks right now. Yeah, okay, so let me go through what it is that happened, because basically what we're trying to do is we're trying to take the embeddings of all, in this case, 3 characters into account into the dense layer. And so what we're doing is we're just stacking them. And so then there's, the network has access to all 6. And so that's that. So we should be able to do model of XB and get an 80. Okay, so cool. So now let's do this, and we have a loss. Perfect. And it's a high loss. It's kind of what we expect. And we should be able to do let's make a big X and a big Y. X is equal to. The problem is, do we really want to render the whole thing? Wait, let's just make these the indices. So this is going to be get batch these indices. Let's see if this works. Invalid index 516. Oh, what? Whoa. So it's between this space and here? That's so weird. Whoa. I've never encountered that before. So if I just called get batch like a bunch of times, whatever. Yes, so inevitably we hit this. Oh, God. Damn. That's a frustrating error. Because we have these weird Unicode, I don't know. I've never had that where a string is not just a. What happens if I do collect of T? C's is probably already taken. So then I do all C's of 516. So what if I join? And then we do 516. What? What the frick, dude? That is so bizarre. String index error. Dude, what? Is there an is ASCII? Look at all these random non. Okay, so we need to fix this. Filter is ASCII T. All right, so we're just gonna get rid of all the bullshit. Okay. So wait, what is X? Y. Okay, cool. So X and Y are the big guys. All right, we're getting somewhere, bro. So now we want to calculate the total loss. I know it's a little bit of an abuse, but let's just see if we can do that. Wait, what is X? What? Wait, what? Something's wrong. I messed up a dimension. Model of X. What is the size of this? Oh, I really did mess that up. What is going on? It's somehow there's a batch size in there. Oh, reshape to oh my god. Wait, we do need that though. Wait, but what we want to do is actually not condition it on the batch size, but we want this to be this. Okay, I think I fixed it. Wait, but it's still wrong. Like ran out of memory or something? What the hell? Let's close some shit. 2 by 3 by big. Okay, so now let's try to reshape. Oh, fuck. Man, that's a big mole. Did I redefine chain? I think I did. Yeah, okay, so EE, reshape EE to be this. What? Re This is what it's supposed to be. 88 by whatever. That makes no fucking sense at all. Actually doesn't make any sense. Oh, I'm stupid. Wait. Oh, I'm stupid. Okay, I got it. We're good. There it is. Okay, cool. That's a big loss calculation, man. That's a big, big loss. What you want to do is you want to calculate a bunch of mini batches and take the mean. In any case, the total loss. Oh, fuck me. Wait. 83? Wait, what's NC? Oh, shit. Oh, did we not? Oh, interesting. Okay. God, I really want to train this. Let's try to train it. Come on. Okay. So let's go to this. And we're just going to copy this. And we're going to modify it. Okay, so n epochs is going to be 1. Let's see, where were we? So we're going to comment this. We already have this. X train. Fuck it. We'll just make it X and Y. Uh-oh. Oh. What? Oh. Here we go. So we need to change this to be X. Okay. I believe, and then this needs to be NC. 10C. Okay. It's kind of shocking that that didn't happen before. All right, then we can delete this. We got descent. Okay. Now I want to actually just test if we can compute the gradient of a batch. Or let's just fucking run it. Oh, these are gonna error. We need to comment these out. This we're just gonna do this. Actually, we gotta get rid of that. We gotta estimate loss. Oops. Okay, but the generate code should work, right? Let's make sure the generate code is good. I don't know if this is gonna work. Damn, it's slow. It's so slow. There's so many batches though. That's the problem. It's stuck in this loop for sure. It's not even in this part, which we. Oh, this is gonna fucking error it too. Damn. Oh, okay. Wait, it didn't learn. Oh no, but that's the wrong. Yeah, that's not that's not the right thing. Let's compute the actual loss. It should be low. It takes so damn long, bro. Oh, what? Something's wrong. Something's wrong for sure. I must have included too much. Because there's no way. So wait, let's try to generate. So it's this. So something's wrong. Okay, anyways, I guess we have the forward pass. The training is not working. Wait, what are the losses? See, that's not right. I think it's got to be a problem with the '83 by '96. What? No, that's not going to work. What? X is like this. X batch. Oh. Wait. Oh. No, X batch is... Yes, we want this. Right, so this is going to be... Alright, so we get losses and gradients. But I don't know why that's so wrong. In any case, I gotta make some food and then study for whatever, an hour. Ay, guys. We're so close. We did the bigram on myself, and then soon we'll do the, because this loss just like, can we just plot losses? This is totally fucked up. Like, obviously that's wrong. So I don't know what I'm doing wrong. Maybe I forgot to offset the Y's somehow. Okay, wait, let's take X. Oh, we didn't do any padding though. We didn't do any of the padding or anything. So that's also partially why the generation is totally messed up. Let's start with... It should start with... Oh. I don't know. Okay, peace out, guys. That was good. I mean, still not fully there on the attention mechanism, but we made a lot of progress the other way with trying to train on the actual data set we want to. So I feel like that was pretty good. Pretty